Good afternoon and welcome you all to the 12th lecture series of STAR 2024. Topic of today's first lecture is Planetary Space Weather, Science and Impacts by Dr. Smita Thambi, scientist at Space Physics Laboratory, ESSE, Tiruvandhuram. And moderator of today's lecture is Ms. Indu Venugopal, a junior research fellow at the same laboratory, that is Space Physics Laboratory, and her area of research is the solar wind interaction with the terrestrial planets. Ms. Indu is currently focusing on the impact of solar transient events on the ionospheric ion outflows from Earth and Mars. Over to Ms. Indu Venugopal.
Good afternoon, everyone. Thank you for the opportunity for introducing Dr. Smita Thambi. So, Dr. Smita Thambi completed her PhD in 2007 from University of Kerala, conducted research at the Space Physics Laboratory, Vikram Sarabhai Space Center, with an ISRO fellowship. Following this, she pursued a JSPS postdoctoral fellowship at Kyoto University, Japan, before joining PRL Ahmedabad. Currently, she holds the position of scientist in Planetary Science branch at the Space Physics Laboratory, Vikram Sarabhai Space Center in Tiruvandhuram. Throughout her career, Dr. Smita Thambi has focused on research in space weather, terrestrial and planetary upper atmospheres and ionospheres. She is actively involved in developing instrumentation for in situ measurements of the ionosphere. Her achievements include receiving the Young Scientist Award at the Asia Pacific Radio Science Conference 2010, URSI GAS 2011, and NASI Scopus 2017. She was also honored with the Young Associate of the Indian Academy of Sciences in 2011 and the Women Excellence Award from SERG, Science and Engineering Research Board, DST, Government of India in 2013. She was honored with the Booty Foundation Award 2021 in the field of plasma science and technology. Within this introduction, I invite Dr. Smita Thambi for her lecture. Thank you. Speaker. Shall I start?
Yes.
Thank you. Thank you. Very good afternoon. Thank you, Indu, and thank you, the organizers, for giving me this wonderful opportunity to talk to the young minds. So in the next 30 to 40 minutes, I will try to give an overview of what is space weather and how it impacts our planetary atmospheres. So when we talk about space weather, first let us try to understand what is weather. When we talk about our Earth's atmosphere, weather refers to the short-term changes in the atmosphere. We think of weather in terms of temperature, humidity, precipitation, and atmospheric pressure as in high and low pressure. So these are basically the state variables to understand our weather. So this weather, which we encounter daily or which we experience daily, happens in the troposphere, that is the part of the Earth's atmosphere which is very close to the ground. And this affects our daily lives. But what we are going to see in this lecture is not the weather of the lower atmosphere, but the weather of space. But now a natural question. The weather of space, why do we care? Because it's too far and too tenuous. Unlike troposphere, where we are having daily contacts. So why do we care? Because space weather can affect technologies. An example is that An unexpected space weather event caused the loss of 38 satellites by Starlink in February 2022. Apart from this, we have seen that space weather can affect the signals from navigation systems, that is like GPS, which can cause degraded accuracy in positioning, etc. And also, energetic particles can penetrate satellite electronics and cause electronic failure during space weather events. So, really, space weather is important to us, and because it affects our technology. So, what is the definition of space weather? Space weather includes any and all conditions, events on the sun, in the solar wind, in the near Earth space, and in our upper atmosphere that can affect our spaceborne and ground-based technological systems, and through these, our life and endeavors. So, this was an early definition of space weather based on the near Earth space environment. But as the humankind progressed, our presence has been increasing to other planets and planetary systems also, and naturally, because of that, our the definition of space weather also expanded to include all natural space environments, not just the Earth's environment. So, what happens when a space weather event occurs? Actually, our sun, or the host star of the solar system, is not as happy as always, and it can really be extremely angry sometimes. And when it becomes angry, it can unleash very violent space weather, that is storms that can radiate enhanced extreme ultraviolet and X-ray radiation into space, and really giant clouds of magnetic plasma. The cloud size can be even bigger than that of Earth. This kind of giant cloud of magnetic plasma can propel into the Earth and other planets as the geometry may be. And then not only this cloud of plasma, it can also spray a lot of charged particles, energetic particles throughout the interplanetary space. And these energetic particles can affect our satellite electronics and so on and so forth. So this is what space weather is all about. Now, let us look into a brief history of space weather, how it all began. So this is a picture in 1580 of a town of Germany. The people then saw a very large and frightening sign in the sky after sunset. They were not knowing what it is, and they didn't even understand what it is. So naturally, they were frightened. And this text, which is shown here, actually continues in a religious manner. They are telling like this is some kind of a magic sign from the heavens and so on. So this is 1580. At that time itself, we had some experience of the impact of space weather on our planet. Now, apart, am I audible? Apart from this,
yes, you are audible.
People have started observing or studying the Earth's magnetism. In this area, Gilbert in 1600 correctly interpreted the deflection of a compass needle. Actually, compass was known to humanity even before this, and it was Gilbert who correctly interpreted that the deflection of a compass needle is due to the terrestrial magnetism, and he stated that Earth itself is a giant magnet. This then actually was an inadvertent step towards understanding space weather in a scientific way. So, not just the Earth's magnetism, people have been observing sun as well. For example, ancient Greeks and Chinese have observed sun with the naked eye. And they have seen that there are dark spots on the sun. The picture what you are seeing here is a full disk of the sun, picture made by Galileo using a small telescope on August 20, 1610, and he has made this picture of sunspots here. So, what are these dark spots seen in the sun, which we now know as sunspots? And people have actually continued observing these sunspots every day. And in 1844, Schwabe discovered that this sunspot has a cyclic or periodic nature. So from a solar maximum, that is the maximum sunspot cycle, to the minimum sunspot cycle is, and then to the next maximum, like that it goes. And the periodicity is about 11-year cycle, which we call as the solar cycle. Now, since people were observing geomagnetic field also and the sunspots, people naturally observed that some disturbances in the geomagnetic field of Earth occur, and these disturbances of the events are connected with the sunspot cycle. So like when the sunspot cycle maximizes, you see more geomagnetic disturbances also. Like wise, there was a statistical understanding or observation, and then happened the Carrington event. Richard Carrington, a scientist, he was observing sun very meticulously and make this kind of sketches of sunspots every day. So it was 1st September 1859, around 11:20 local time. He saw that two patches of very intense bright white light broke out in the positions A and B marked in this picture, that is near a sunspot region. And then he saw that it was so bright a flash. So he just reported that, and then around 17 hours later, there was a great geomagnetic disturbance which actually disrupted a lot of telegraph services that day. So people naturally thought that this could be a sun-earth connection. So whatever unusual episode Carrington has observed could be having some bearing on what has happened in the geomagnetic field and telegraph service center. So there was a discussion that it could be sun-earth connection, but some people even then told that this could be mere coincidence. Then came a very seminal discovery, or a very profound discovery which really changed everything. That is, in 1908, Hale discovered that sun is a magnetic star. He wrote a report he reported that on the probable existence of a magnetic field in sunspots. So he identified that these dark spots which we see in the sun, on the sun, are really connected to the magnetic nature of the sun. And basically, sunspots are the manifestations of the solar magnetic field. Now, this is such an important discovery that that even the substantial fraction of even today's work in solar physics and space weather, including all our observations, many of our observations and modeling, are devoted to understanding these enigmatic magnetic field variations in the sun. In this picture, what you are seeing here is a sunspot, which is in the visible light. These dark spots which you are seeing are the sunspot. And then in the right, what you are seeing is a magnetogram measured by a spacecraft. So wherever you see a sunspot, you can see the magnetic field, positive and negative polarity fields, which are related to the sunspot. So sunspots are basically manifestations of our solar magnetic field. Now, if a sunspot is a manifestation of a solar magnetic field, then obviously the sunspot cycle is actually a solar magnetic dynamo cycle. This people have understood. And then in the 1930s, Bertels, what he has seen is that during solar minimum also, he found a lot of geomagnetic storms occur. And when he closely analyzed the data, he understood that these storms have a 27-day periodicity, which is same as the solar rotation period. Now we understand them as co-rotating interaction region, which is a cause of major space weather event during low solar activity. These co-rotating interaction regions are high-speed streams originating from the coronal holes of the sun. So by these kind of studies, we have established that there is a definite connection between what is happening in the sun and then what is happening at the Earth or Earth's geomagnetic field. So the connection is that both have their own magnetic fields, and probably the interaction is what is causing space weather impact. Now, with that understanding, let us see the driver of planetary space weather, that is the sun. When we mask the solar disk during an eclipse, naturally, we can see its atmosphere, outermost solar atmosphere, that is called corona, which is a fully ionized plasma with magnetic field that is millions of degrees hot. So this region, which is a fully ionized magnetic plasma, can emit extreme ultraviolet light. For example, the ionized helium can emit at 30.4 nanometer. To compare, visible light is around 400 to 700 nanometer, as you know. So once this UV light is emitted, these can actually affect our planetary atmospheres. That's what we will be seeing now. So before that, not only UV radiation, sun emits in the other wavelengths also, and this picture shows a solar spectrum. Average value of the spectral irradiance plotted in the y-axis and wavelength in the x-axis. So you can see X from XUV to IR, and this actually matches with a Planck's black body model with an effective temperature of 5,800 Kelvin. And we can see in the bottom axis the relative variability, how much it varies over a solar cycle. So you can see that the axis goes from 10 raised to -2 to around 100. And then we can see that visible or IR have very little change over an 11-year cycle, which we also know. We don't notice a substantial change in visible or IR radiation because a sunspot maximum or sunspot minimum time. But when we see the extreme ultraviolet or the X-ray radiation, etc., it has around 100% or more variability from when you compare a sunspot maximum to a sunspot minimum. Now, with this understanding, let us see how it arrives the Earth and other planets and what the planets have to offer to this incoming radiation. So we know that these are the planets and these have atmospheres with different composition. As you can see, Venus and Mars have a carbon dioxide dominated atmosphere and Earth has a nitrogen dominated atmosphere. As you might have heard in the last lecture, the gas giants have hydrogen and hydrocarbon dominated atmospheres. And these and according to the sun planet distance, the solar radiation also arrives with longer times, takes longer time to arrive at farther planets. And this, not only these planets have atmospheres, some of them have magnetic field, intrinsic magnetic field too. For example, Earth has a dipole magnetic field, which Venus doesn't have. Mars has a very weak crustal magnetism associated with that, whereas all these gas giants have their dipolar magnetic fields. Now, with this kind of a background, when a solar radiation, the extreme ultraviolet and soft X-ray reaches these planets, it does something very drastic. That is, this UV radiation can ionize the planetary upper atmosphere, creating an ionosphere of planet. This is a partially ionized plasma seen in every planet. Now, this picture shows an example of our own Earth's ionosphere, which starts from around 80 kilometers and goes to very high altitudes. Now, the lower altitudes are known as the D region, then E region, and the highest degree of plasma is seen at the F region. The F region stays even during the night side because of the longer lifetimes of recombination of these ions to again back to neutrals. And then we have the D and E regions mostly disappearing during the night. So this is basically the impact of solar radiation into a planet. Now, as I told, not only the radiation, sun emits particles or plasma and magnetic fields also, and this magnetic field is what we call as the interplanetary magnetic field, which is basically the solar magnetic field. And this is the typical velocity of solar wind measured by Ulysses satellite. The uniqueness of Ulysses satellite is that it went out of the ecliptic plane even and measured the solar wind at different latitudes of the sun. And it found that The typical solar wind speed is around 400 kilometers, whereas the high-speed streams from the higher latitude regions can reach up to 700 to 800 kilometers. This is a non-eruption case. Now, this solar wind and the magnetic field associated with that also reaches several planets. So here is and as the sun-planet distance increases, the magnitude of the solar wind density as well as the IMF, that is interplanetary magnetic field magnitude, reduces. And the arrival time also increases as the sun-planet distance increases. So around 4 days, typical solar wind of 400 kilometers per second takes around 4 days to reach Earth. Now, with this background, we understand that it is the solar magnetic field which drives the solar storms. So let us have a closer look to the sun and the solar magnetic field. This is an ultraviolet image of the sun, which reveals the loops of hot ionized gas trapped in magnetic fields. So as the sun rotates with differential velocities, these kind of magnetic fields can get entangled, break apart, and when they break apart, they release magnetized plasma. These plasma, what you're seeing here, will be released, and this is the major cause of severe space weather. So what are all these solar magnetic eruptions can cause? The solar magnetic eruptions, as I told, is caused by the sudden magnetic reconnection in the solar outer atmosphere, where this magnetic fields can get entangled and break apart. And then this happens in the chromosphere or corona and corona, and which can be seen as flares, associated electromagnetic radiation with the explosion. This can emit from radio waves to even gamma rays. And then the plasma cloud, which is erupted, can also reach planets with giant clouds of magnetic plasma. Then we call them as coronal mass ejections, with maximum speeds can even exceed 1,000 kilometers per second. And that is why the Carrington storm reached the Earth within around 16-17 hours. Apart from this, highly energetic particles can also be emitted or accelerated during these eruption events that we call as SCPs, which are a concern to the satellite electronics. So let us see how a coronal mass ejection looks like. This is a typical coronal mass ejection, which carries actually billions of tons of coronal material and embedded magnetic field. And so this it can be even slower than around 300 kilometers also sometimes, and the fastest can be around 2,000 kilometers per second, as I told, and which can reach our planet within hours. But solar flares, which are actually the brightening of a region of sun, typically lasting several minutes. And as we know, the solar radiation, because it is electromagnetic radiation, as I told earlier, it can reach our planet within 8 minutes. Earth case, and then this can actually give out a lot of energy in a short time. So the solar flares are visible in white light, as Carrington observed, but they are very often readily noticed in their bright X-ray and ultraviolet emissions. What we see here is an ultraviolet image of the sun in November 2003, which was a very intense storm. So what happens when a solar storm hits? As I told, Earth is a giant magnet. So assume that Earth has a bar magnet placed inside that. Then it should be, if you trace those magnetic field lines in space, it should look like this, a very symmetric dipolar magnetic structure. But in reality, this doesn't look like that. The solar wind makes the Earth's dipole magnetic field into a different structure. The day side is getting compressed and the night side is getting stretched. This structure we call as the magnetosphere. And one more interesting point to note here is that at very low altitudes near the surface, the dipole structure is preserved. And Because of that, the solar wind is not entering directly into these regions. So the magnetosphere actually shields the Earth from the direct entry of solar wind particles. Now, sometimes when a solar storm occurs, sometimes means when a solar storm occurs, this doesn't happen. What happens is when the direction of the solar wind field, magnetic field becomes exactly opposite to that of the Earth. And here what we can see is because it comes at two opposite polarities, this gets cancelled, and then there is a opening of the magnetic configuration through which the particles can really go inside. So for a short time, this magnetic flipping or the magnetic field, the solar wind magnetic field becoming southward, opens up a gateway for particles to enter into the Earth's magnetosphere. And the amount of energy released by this process can be formidable. And this process is called magnetic reconnection. Now, once the plasma sees a magnetic field line, it starts following these field lines, and the particles can eventually reach the upper atmosphere of planets. Now, before going into that, let's sphere away, and that is one of the major mechanisms for atmospheric escape of a planet like Mars. Now, going into the impacts, again we will take Earth as an example. The solar flare impact, actually what happens when a flare hits, the X-ray and ultraviolet radiations increase by orders of magnitude during large flare events. So ionization also can suddenly increase. And when there is a sudden increase in the ionosphere down to the D region, the radio waves can be absorbed. This impact radio communication, or this can disrupt radio communication. For example, if you are using an HF radio for communication, then this can be disrupted. And then, as I told, the giant magnetic cloud, if it comes and hits the Earth, there commences a geomagnetic storm. And in the 1990s itself, we have understood that the magnetic reconnection is a process by which the geomagnetic storms occur, or the solar wind really connects with the Earth's magnetic field. So, as I told, when the storm comes towards us, the reconnection occurs, and then these particles find their way to the Earth's upper atmosphere. And then these particles also causes enhanced ionization and excitation, and then this excitation can emit lights of varying color and complexity. So this is what we observe as aurora with different colors, that is green, red, etc., and also in the other wavelengths also. And following the impact of a CME, because a lot of charged particles come, the intensity and the extent of the aurora increases. And just a point note here, this auroral oval, where most of the particle precipitation occurs because of the field line geometry, is not centered at the geographic pole, but at the geomagnetic pole of the planet. So I just want you to think about how aurora will look like in Mars, because in Earth we have the field lines to protect us in the Earth's equatorial and low latitude region, whereas Mars doesn't have a global magnetic field. So just think about it, how aurora will look like in Mars, and you will see a lot of images of Mars with what kind of aurora you will be seeing if you just Google. I'm not going to show it, just I just want you to think about it and find it out. So just let us go into the physics of geomagnetic storms. Basic understanding what we have with our electrodynamics is about a changing magnetic field generates an electric field. So that's Faraday's law, Maxwell-Faraday's law, del cross E is equal to minus dou B by dou T, where this is the partial time derivative, and this is the electric field which is generated. Now, as we saw, the solar wind, when it interacts with the Earth's magnetic field, our Earth's magnetic field changes. And then we have, so then that means there should be an electric field which is generated. Now, Ohm's law says that this electric field in a conductor can create an electric current. J is equal to sigma E, where sigma is the conductivity. And if you have a moving plasma in a magnetic field, that also creates a current which is U cross B. So there is a current which is generated in a conductor. So what are the conductors in the case of space weather? That is, one is planetary atmospheres. Another one, Earth's lithosphere or surface is also a good conductor, which can actually cause what we call as geomagnetically induced currents. This has huge impact in terms of space weather, especially in the high latitudes where your conductivity enhances significantly by the particle entry into the upper atmosphere. For example, on 13th March 1989, the Canada had a power grid which crashed because of a space weather event, and 6 million people lost electricity for as long as 9 hours. And later on, we understand that this was caused by a space weather event. So this is a technological impact even at the ground level. Going into the low Earth orbit, we already know that J is equal to sigma E plus U cross B, where you have a plasma which is moving with the velocity U, and we have the magnetic field, and the changing magnetic field has generated an electric field. So electric currents are now generated in the ionosphere, which is enhanced during a storm time. And then this ionospheric currents can heat and expand the thermosphere. The thermosphere is the neutral counterpart of the upper atmosphere. As I told, the ionosphere is not a fully ionized plasma, it is only a partially ionized plasma. So it can actually expand, the currents can heat and expand the thermosphere, and then the expanded thermosphere can cause an increased drag on satellites at low Earth orbit. So increased drag can change your satellite orbits. This is very important as the number of satellites in the LEO has doubled due to these mega constellations like Starlink, OneWeb, etc. So now with this understanding on space weather, can we really see what happened to those 38 satellites in February 2022? What happened is as follows. On January 29, 2022, the sun gave out a very moderate flare and a related coronal mass ejection. And this material reached the sun. From the sun, it reached in a few days at Earth. Now, on February 3, the Starlink launched satellites to a parking orbit of around 210 kilometers, which has sufficient amount of density in the thermosphere. So this thermosphere, due to the presence of these currents in the currents due to storm, the thermosphere had heated up, then enhanced the drag, and this enhancement of the drag was around 50%. And this actually prevented the satellite orbit-rising maneuvers, and eventually the satellites were re-entered to the Earth's atmosphere and lost. Actually, the important factor is that though we have observations of the sun and the flare, etc., no forecasting model could predict this 50% of enhanced drag, or this much a moderate flare could cause this much havoc at these altitudes. So this is how the 38 satellites were lost, which was really an alarming sign of how important space weather is. And also, solar energetic particles can penetrate satellite electronics, as I told, can cause failures during space weather events. So to summarize, understanding and forecasting space weather is essential for safeguarding our technology and enabling safe space exploration to Earth and to other planets. For that, we need observations of the sun and planetary ionospheres, magnetospheres, etc., and model simulations to calculate parameters like drag, etc. So the solar observations are provided by several satellites like ACE, WIND, SOHO, our own Aditya L1. These are at the L1 points, and Parker Solar Probe, Solar Orbiter kind of satellites go very closer to the sun and observe them. And we have several satellites to study, observe planetary ionospheres and magnetospheres as well. So with this, I conclude. Thank you.
Thank you, ma'am, for the talk. So next we'll go to the discussion session. So the first question is, why did D region and B region differ during the night?
Okay. That is because of our the ionospheric constituents and their recombination rates. For example, in the lower regions are more having molecular ions rather than atomic ions, and they recombine in a different way compared to the atomic ions. Atomic ions give like oxygen O plus radiatively recombine. It's a slow process. So the ionosphere, though reduces in density, stays longer in night because the atomic oxygen or atomic ions dominate in the F region, whereas the molecular ions can recombine very fast, so we don't see them at night.
Okay, coming to the second question. How do the magnetic fields affect over the poles, causing aurora?
What happens is, unlike equatorial region where the magnetic field lines are closed and particles do not directly enter into the Earth's upper atmosphere, we have the open field lines or open field lines during the polar region, which is directly connected to the solar wind. So once this particle comes, this magnetic field lines are basically equipotential surfaces, so they can just come down to a region of the atmosphere where it can give out energy by collisions, or it can ionize particles and so on and so forth. So once it excites any molecule or ionizes and excites, then they can give out this additional energy. If it is in the visible, we see them as red aurora, green aurora, like that.
Okay. Next question is, does the space weather affect largely in the satellite data collection?
The space weather affects the satellite electronics in such a way that they can cause single event upsets or single event latches. So if a single event upset occurs because of an energetic particle in that, for a short duration, the electronics can be disrupted, or it may require a restart and so on. So in that way, it affects the electronics, and if the effect stays longer, then it can really affect the data collection, etc.
Okay, coming to the last question. How much damage could solar wind do to our magnetic field?
Yeah, it's not really damage. What we see is the first is that structure itself is changed from a perfect dipole to a structure which is compressed at one end and stretched at the tail end, which we call as magnetic field. And secondly, what we see is that when a opposite polarity comes, it opens up the magnetic field for a short time. Afterwards, it comes back to its original configuration. So it's not like a permanent damage. The space weather events are transient, so the effects are also transient.
Okay, I think that's all questions.
Okay, thank you, Ms. Indu, for nicely moderating this session, and also my gratitude and thanks to Dr. Smita Thambi for a wonderful and a very informative lecture today. Thank you, both of you. And I think the next speaker is also.
Thank you. Thank you so much. And best wishes to all students. Thank you.
Thank you. Now we will.
its implications for space exploration. So she basically studies how microorganisms interact with these minerals or electrodes, and in very unique environments, shedding light on fundamental biological processes active on the Earth's subsurface or very deep within the surface of the Earth. And this knowledge is starting to now steer technological advancements that are crucial for these very long-term space missions and on planetary surfaces, right? That's just like, for example, Mars or these other very fascinating planets. And at IIT Kanpur, she continues to push the boundaries of scientific knowledge, bridging the gap between microbiology or geobiology and space exploration. And she hopes to inspire future generations of researchers to explore this very novel frontier of astrobiology. So without further ado, I think, Yamini, the stage is yours.
Thank you, Kunal, and thank you, Praveen, Kunal for introducing me so wonderfully, and Praveen for actually inviting me here. I just wanted to confirm that the slideshow is visible properly and I am audible.
Yes.
Okay, great. And okay, so warm welcome to all the students to this platform. I think it's a wonderful opportunity for you to learn about all the science which is happening in the realm of space. Today, I will be focusing on life in the solar system and linkages to exosolar planets. The outline of my talk, and let's see, is going to first identify what Earth life is like, can be defined based on what is present on Earth, what could be life on other planetary objects, what are the basic requirements of life, what are the molecules, and can those macromolecules be divided into basic elements? What were the origin of these basic elements in our universe? What is the geological history of the Earth? And how these basic elements actually came about to become these macromolecules, which is life for us. And whether these life which is present on Earth can survive in extreme habitats. What does habitat mean? Is an environment where you can survive and grow. So what are extreme habitats? Something's very hot, sometimes it's very, very cold, very high pressure, low pressure, no nutrients. So can microbes or life on Earth survive in these extreme habitats? And going on from there, are there extreme habitats present in our solar system? And from there onwards, we will focus more on what kind of habitability might be present on Venus. Is there a past life or present life biosignature on Mars? What are these icy worlds we are talking about? And exoplanets. Okay, we found them. How would we characterize the habitability of these exoplanets? So I know it's very vast. So please tighten up your seatbelts and we'll hope to cruise through this. So I think when we think about life, it's mainly, as astronomers, I think we come from this mindset of, okay, humans will be there, maybe animals, maybe trees, but what we always forget is about these unseen microorganisms which are present. They are present on the palms of our hands, in the biofilm of our teeth. They are present in our stomach, gut. They are present pretty much everywhere. So over here on the left, we can see that this is a microbial community. I have colored them falsely with pink, green, yellow, and they are actually surviving on these electrodes. Electrodes are nothing but, carbon, which is actually poised or, has a potential of a certain value, which can mimic the environment reducing potential. So whatever the environment might look like, we can actually mimic that on the electrode. And here I am showing you a hydrothermal well. These are like little magma or hot exposure of water which is coming from the deep subsurface of the oceans. And over here, you can see that beyond these microbes, you can see these tube worms. These are eukaryotes. These are little animals which are surviving without light. So how are they actually surviving so deep below the surface of the ocean with no sunlight and pretty much minimum nutrients? So let's go on by defining what life is written as by NASA. So NASA actually defines life as a self-sustainable chemical system capable of Darwinian evolution. So if we ever go to exoplanetary systems or even extraterrestrial systems, what kind of life will be there? They have to be self-sustainable, and they have to be Darwinian. They have to have evolution. So this is a very limiting definition. So will a presence of virus which cannot replicate without a host not considered life? Are they not living? As in, we know that they are not living, but they definitely have the potential to live as long as they are associated with a host. So as we move forward, we have to really understand that the canonical characteristic of life are inherently the capacity to adapt to a changing environment, and whether they can interact with other possible living organisms in the environment. So moreover, the definition of this life has evolved. We know that NASA just defined it very simplistically with saying that, okay, we have a self-containing, self-sustaining system, and we have Darwin evolution. Later in 2002, which is not many years back, Briadani and Koshland said that it has to be programmable, it can improvise, that means it can actually interact with the environment, it has to be compartmentalized, actually separate from the environment somehow, it has to derive energy, it can regenerate, maybe it can actually replicate, it has to adapt, and slightly secluded. So these are the 7 pillars of life, which was defined by Koshland. And if we sort of combine these two in broad aspects, in 2007, the National Academy of Press actually released this nice little statement that any life has to have a way of deriving energy from its environment, should be able to maintain some bonds between elements, should have a liquid environment which can act as a solvent, and possibly have a molecular system that can support evolution. Evolution is not necessary, but this is all actually in the decreasing order of certainty. Like how often and how confidently can you define life? So in 2019, we have this very succinct definition of life, that a life is very far from equilibrium, self-maintaining chemical system capable of processing, transforming, accumulating information acquired from the environment. So what are the basic requirements of life? Of course, we have to derive energy. These energy can be derived from redox reactions. So actually you can take energy from lactate, transfer the electrons from lactate all the way to oxygen and giving you the highest amount of energy. You can also derive energy from sunlight, and we of course don't do that, but trees and many organisms do that, where they actually take in a very small amount of energy from red and infrared light and pump electrons from low energy environment to a high energy environment. And then when you drop back, you have an electron donor which accepts electrons. And this way you can derive energy. And the next important in the requirement of life is encapsulation. So you have to have this really nice molecular machinery encapsulated from the environment to permit maintenance of stability within a very chaotic environment. So while you have stability within the environment, the entropy of the overall system is increasing. Finally, and possibly when you learn, life is always learning from itself, you probably have the capability of self-replication using a genetic code, and it might be subjected to natural selection. So this is the central dogma of life, and you can see that to maintain all these requirements, you need macromolecules. So we have carbohydrates, which for example is cellulose, which is made up of carbon, oxygen, And we have chitin, which is the structural element of a lot of copepodids, and say, for example, shells of crustaceans like crabs and lobsters. They are made up of carbon, nitrogen, and oxygen. You have proteins where we have nitrogen and sometimes sulfur in form of cysteine. There is amine, we have a peptide bond. We have phospholipids, which actually form the outer membrane of our microbial cell. You have these nucleotides and nucleic acid like ATP, ADP, and DNA and RNAs. And what I'm trying to tell you over here is that these are nothing but basic elements, which is, for example, carbon, hydrogen, oxygen, nitrogen, sulfur, which is present in cysteine, and phosphorus, which are bound very intricately with covalent bonds, for example, sometimes hydrogen bonds within the nucleic acid, ionic bonds in proteins to make it more electrophilic or electrophobic. So all these are really important necessities of actually defining life. And here, so basic elements of life, I would like to, and in literature has been divided into 6 different elements, which is carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus. And you can see how our macromolecules have incorporated them in their system. And if you look at a bacterial cell, which is the smallest cell which we can see, majority of this, which is gray in color, is carbon. And when you zoom in, you have oxygen, which of course we know that the CHO, which is is really important in all our macromolecules, and then hydrogen, then we have phosphorus and nitrogen, sulfur, and then these smaller elements, which I call minerals. So metal ions are really important. They catalyze metabolic reactions, they stabilize the protein, they form gradients across the membrane, and they mediate signal transduction. And what I am very interested in is forming this, aiding in electron transfer processes. But where did we get all these elements from? So in the cosmic history of the universe, of course, we know that, this is an active area of study, but as of now, what I understand is that Big Bang fusion actually brought us hydrogen, and then we have helium, where we have contributions from Big Bang fusion, and we have exploding massive stars which can produce helium, and we can also have dying glowing low mass stars which can produce helium. And similarly, lithium, beryllium, boron actually come from cosmic ray fission. So it's all there. This is called stellar nucleosynthesis, and it was already present or is being formed continuously in our universe. So what is important to see is that these stable elements, when you rank in order of percentage of mass, so in the cosmic universe, of course, we know hydrogen is most present. I just wanted to know whether my laser pointer is visible. If not, oh my God, it's visible now. I am so sorry. Okay, so hydrogen is most abundant, followed by helium, oxygen, carbon, and then we have other elements which follow us. In the Earth's crust and Earth's ocean and the atmosphere, we again have a lot of oxygen present. We have hydrogen, we have a lot of argon and noble gases present in the atmosphere. And if we compare that with the humans have very well actually adapted, or even microbes have adapted to take up a lot of carbon in their system and oxygen in their system. So there's more oxygen in the system, and there's a lot of carbon in their system. So how did biology was able to grasp all these basic elements from Earth, which was present, which came from the cosmic expansion of the universe? So we know that the formation of Earth happened about 4.5 billion years ago, and then the formation of Moon probably happened 4.527 billion years ago. And there were these late heavy bombardments, which we probably think is because of meteoroids and asteroids hitting the surface of the Earth. They probably brought some carbonaceous material to help flourish life on Earth. these are all hypotheses, and it can also come from within the Earth. So this is all an active learning and research happening in the science right now. So again, we have, whatever the reasons are, Earth life, the biosignature of the first life was observed about 4.0 billion years ago, and the earliest start of photosynthesis. So photosynthesis is actually using sunlight to form oxygen, right? That happened 3.2 billion years ago. So what is happening here? When the first life was actually around 4.0 billion years ago versus the first sign of oxygen, what was happening in between these two regions? So I really was perplexed that when we started as planet, a lot of our seawater which was present on Earth was iron rich, and we had many more other chemicals which are present on the surface of the Earth. And as the metabolisms of microbial communities evolved, we had more and more oxygen present in the Earth. So here you can see that 4.0 billion years ago, we had a lot of iron in the sea, and as the microorganisms evolved and tried to learn how to make oxygen using anoxygenic photosynthesis, we got a little blip of increase of oxygen in the atmosphere. So on the top panel here, you can see how much oxygen was present on the Earth and how much minerals were present in the sea. And we can see the first blip of oxygen actually came from first organisms which were capable of probably respiring oxygen. So we had some oxygen producing, but there were some organisms which were also respiring on oxygen. So there was first blip happening, and then we had more and more oxygen accumulating on the surface of the Earth, and our oceanic system, the oceanic subsurface also was now rich in oxygen. So how do we understand that where these biomolecules, which were carbon, hydrogen, nitrogen, oxygen, and phosphorus and sulfur, how did they actually come about to form these nice little macromolecules for sustaining life? So there is, of course, this really interesting project which Miller and Urey did, where they have this nice borosilicate chamber in which they assembled an atmosphere which mimicked the environment of early Earth, and they were able to make a lot of amino acid, which was probably present in a meteorite also. And so they were able to see that. But what has now come into the picture is that could the borosilicate glass present in Miller-Urey experiment have an effect on what came about in the discharge experiment? So it really depends upon which researcher you're talking to. There are two ways of thinking about how life originated on Earth, whether it was geochemistry, everything happening in the atmosphere, or whether it was biology down approach. So whether Darwinian evolution was more important, whether you needed the building blocks of energy first, or whether you had to make something to actually catalyze all these reactions happening in a microbial cell, or was there no point of genetic or metabolism without compartmentalization? So what is most important? Whether compartmentalization is important, the genome is important, the proteins are important, or the metabolism? So it really depends upon who you talk to. They will tell you that RNA might have come first, or whether the metabolism might have come first, or the protein world, or the people who believe that encapsulation happened first. And it really doesn't matter what really happened first. It could have been happening together. But what really appeals to me is that every life is nothing but actually transfer of electrons, right? So when you transfer electrons from a protein molecule to another protein molecule is when you generate ATP in a biological cell. So coupling of electron transfer reaction actually forms ATP, which is mediated by this proton electrochemical gradient. Where can you find this proton electrochemical gradient? Inherently present in the Earth system. You can look at it under the deep subsurface. So in the ocean benthic floors, there are these hydrothermal vents, where you have these geochemical gradients present. So you have a very alkaline hydrothermal fluid versus acidic seawater during the early Earth system. And when you have this gradient across a complex structure of metal and minerals, you can form initial macromolecules. So this person, Nick Lane, I would really suggest you look at his YouTube lectures. It's really interesting. You can actually make macromolecules, very similar, simple formate and glucose macromolecules by just combining carbon dioxide and hydrogen across a geochemical gradient. And this happens a lot in these hydrothermal vents. So the first image I showed you of tube worms present in the deep subsurface is happening without sunlight. All this energy is being utilized and it comes from organisms which are living without sunlight, and they are living using proton electrochemical gradients. So geochemistry of these hydrothermal vents is giving rise to biochemistry. We could have had first protocells being formed, and then these protometabolism, which is the initial form of metabolism. And then these proton metabolism led to some RNA polymers, which is the RNA worm. And we have these polypeptides being formed. And finally, we have a molecular machinery, which is encompassing within these microbial cell. And then our first LUCA, which is the least common ancestor, least universal common ancestor. So I think what I would like to say is that when you look at the thermal fluid versus seawater, the organisms are literally surviving on hydrogen and carbon dioxide. And it's a very reducing environment, which was the environment of early Earth. So I hope I have convinced you that probably hydrothermal vents were where life originated on Earth. And those kinds of environments still exist on Earth. So it is very well said in the marine community that humans and humankind know more about space than they know about the deep subsurface of the Earth. So I think it is, and if you want to understand life and how life might originate on other extraterrestrial planetary bodies, we must look deep inside the Earth subsurface. Okay, so again, going forward, this slide just tells you that microbes were the first organisms which actually came about, say, for example, 4,000 million years ago, and they are still surviving. They're still surviving through all these mass extinction and probably will survive through climate change. So we need to understand how microbes have evolved and actually brought about life on the Earth. So again, moving forward, Earth is a planet of extremes. While on the surface, we don't see it because we have this really nice atmosphere which is protecting us, and we are not living in the deep ocean where the pressure is so high. So the pressures in the Earth can reach up to, say, 1,000 megapascals, and we have varied environments of pH, we have varied environments of temperature and a lot of salinity. So how much salt is present? Of course, seawater is more saline versus fresh water. But humans can, and again, I'm not saying that we have humans living in this plot here. So humans can survive at 0.1 megapascal. Our blood is about 6.7 pH, and the temperature, of course, room temperature 28, 30 degrees Celsius, and we drink water, which is about 4 NaCl, right? But Earth life, which is the microbial life, unseen microbial life, has more extremes present. So they have been shown to survive in very low pressures, very high pressures, of course. The hydrothermal vents, they are very high pressure environments. They have survived in very alkaline environments and very acidic environments. They have been able to survive at very low temperature and extremely hot temperature, for example, in Yellowstone National Park, and hot sulfur geysers of Ladakh. And we have very huge salinity also present where microbes can survive. And these kind of diverse extreme environments are also present on inside our universe, right? So we have Venus, which we do not know much about the salinity, and we have Earth, we have Mars, where salinity has been predicted. We have all these moons of Saturn and Jupiter, where we have characterized what the pressure looks like and what the pH looks like. So can there be life in these planetary bodies in the solar system? Again, so we have to focus on the atmosphere and how the atmosphere of the solar system differs from the Earth. So they are all very different, of course, you would have seen. But let's focus on the Venus first. So the Venus has a lot of carbon dioxide. We have very little nitrogen compared to us. And there is a lot of sulfuric acid. Sulfuric acid technically is considered toxic for life, but there are microorganisms which can survive in acidic environment. So could there be life on Venus atmosphere? So if you look at the atmosphere and how the atmosphere changes, how the temperature and the pressure of the atmosphere above the Venus surface changes, there is a really nice sweet spot. So right above 60 kilometers, you have this, right above this 60 kilometers, you have a temperature range which is very ambient for us and a temperature range which is ambient for microbes also. So could there be any life which is living in these atmosphere in form of bioaerosols? So I know there has been much debate on the detection of phosphine in the Venus atmosphere. Phosphine as a biosignature is again debatable, but just to put it out there, phosphine can actually come from mineral phosphate by phosphide production, and that can be reduced by anaerobic metabolism to actually produce phosphine in the system. So there are microbes that can do that for you, and that is why Sarah Seeger, who was the main author on this paper, observed phosphine in the atmosphere of Venus from two different telescopes, ALMA and JCMT, and tried to inform us that there could be presence of phosphine in this environment, and it is important for us to explore Venus more further. So here again, I'm showing that could there be some microbes living in these encapsulated environment in the bioaerosols of the Venus atmosphere. Of course, NASA is never behind in exploring all these habitability questions in the solar system and beyond. So they are sending a lot of flybys and in situ analysis. They in fact have a balloon program where the outside is made up of titanium to save the entirety of the shuttle from sulfuric acid, and to be able to sample the atmosphere of the Venus. So now moving on to Earth, Mars, and how it is, how close it is to Earth in size, and also of course, all the planets were born together. We believe that it has a lot of mineral matter which could support life, because, again, microbes are able to transfer electrons from a mineral to a mineral. So can microbes, or may have they been present in the early days, or early, not days, but early Mars? So again, we can see that while we have Earth here, we have oldest minerals and oldest rocks, we have the anoxygenic environment which converted into oxygenic environment, and we have these really nice pictures of the Earth environment looking into the past of the Earth, and where we can actually find what GOE, or the Great Oxidation Event, looks like. On the Mars, there are a lot of unanswered questions. What was the magnetic field like? Were there any hydrothermal activity? And were there any intense impact or bombardments? And could there be any signatures of life on the surface of the Mars. Moreover, we have discovered that Mars hosts a lot of hydrous minerals. So you have hydrous clays, you have hydrous sulfates and carbonate salts present on the surface of the Mars. So while the atmosphere is very thin and you have a lot of sun exposure, so surface might not be able to host any microbial life or any form of life for that matter. Could there be life in the deep subsurface? For example, if we drill a core, or take, say, 5 meters or 5 centimeters of the core on the surface of the Mars, can we find signatures of current or past life present on Mars? So moving on to these icy worlds, and these are very far from Earth and of course from Sun, and that's why some of these moons of Jupiter and Saturn host very high and deep ocean environments, which are possibly directly interacting with the rock or the crust at the center. So there are this knowledge that we have these, of course, there are photographs being taken that there are plumes which are coming out of the surface of Europa and Enceladus, both which are the icy moons of Jupiter and Saturn, respectively. And could there be any hydrothermal vent-like feature which could be present at the deep subsurface? Again, reminding you, Earth subsurface Earth ocean is not very deep compared to what we are looking at here. Here, the deepest we go down to is 100 kilometers. So what kind of instruments will be required to look into that deep water rock interaction? So NASA is sending Europa Clipper mission, where they are going to incorporate some radar instruments to see how deep this the depth of rock and water profile could be, and whether they can map any gases coming out from these environments using mass spectrometry. So one hypothesis is that the olivine and water which could be present in the rocky core can produce methane, which is probably an abiotic source of methane. And once you have these methane can possibly come out in the form of plumes, because methane was detected on the surface of the Enceladus ocean. So the next question is, if we have methane, can there be any methane metabolism? So microbes of the early Earth have been shown to metabolize methane, so which is called methanotrophy. So it is important to figure out that whether we can have any microbes present on these environments. So NASA is again sending and identifying all these ocean worlds which are present within the solar system, characterizing these oceans, what kind of solvents may be present, what kind of rock-ocean interface is present, and would there be any energy for life? So for example, we need to understand that if there is life, where are they deriving their energy from? What kind of environment is present? And finally, searching for life. Well, can you just take an image? Just an image will tell you whether there's microbe present or not. So this is an area of active research of how to identify potential biomarkers in extraterrestrial system. So moving on, we have, of course, these exoplanets. There are different kinds of exoplanets, and about 5,000 of them have been found, which are planets, like Earth, or gas giants, or maybe super Earth, or probably Neptune-like, which has a lot of water, warm water on its surface. They have been characterized in this exoplanet archive. We have to identify which one of them would be habitable. So of course, there are various ways of identifying exoplanets. There's radio velocity transit, which was led by JWST, actually works on the principle that when a planet comes in front of the star, which it is associated with, the atmosphere or the emission spectra or the transmission spectra which is received on the Earth or by the telescope changes. So, and whether there is a duration to that change, and this sort of helps us identifying whether this is a planetary system or not. But to sort of understand or even speculate whether this exoplanet may be habitable, there are various questions and answers to be given, right? So whether it is a minor planetary system, does it have exomoons? Will there be dust storms on this planet? What kind of atmosphere there is? Whether there is any stellar effects. So what is the rotation like? What is the magnetic field like? Are there any cosmic rays? Because if there is any cosmic rays and if there is no atmosphere, of course, the surface will not have any life. If we look at the biology aspect of it, we have to study the atmosphere, which is the albedo. We have to understand what is the mass and the radius. We have to understand what are the temperature, composition, and weathering effects. Whether there is any UV shielding, and whether there is any kind of climate. So all these studies will actually inform us whether there's any habitability possible in these exoplanets. And very briefly, Sarah Seeger in 2013 sort of identified that we have, if you want to see whether they're Earth-like and if they're habitable, we can look into how the radius of the orbit looks like compared to the Earth versus how the mass of the star is relative to the Earth. So if we look at this habitable zone, which is blue, we can identify which of these exoplanets are possibly habitable for any search for life. One second. So with that taken into picture, of course, there is Kepler 432 system, which is pretty much, the sun is about twice as big as the Earth sun, but the star is twice as big as the Earth sun. And then we have the distance about the same as Earth. So this is a very popular planetary system which is being studied for exoplanet habitability. So again, coming to transmission spectroscopy and how the planets orbiting around the sun can help identify what kind of atmosphere which is present on that planet. So this is a work from JWST. Of course, you can see that the wavelength actually spans from IR all the way to close to UV, and you can see that a lot of little elements, biologically relevant elements, were identified in the spectrum. So NASA is sending again a large UV optical infrared instrument to identify various planetary system and their absorption transmission spectra, and to figure out whether there could be, or what kind of atmosphere might be present in the planets, and whether it can be habitable or whether there can be any life in the system. But we need to take all these research with not a grain of salt, but with some understanding that when any research is reported, we need to understand it should tell us the status of life detection, whether you have detected some kind of biological activity. Can you rule out the contamination present in the spectra or otherwise? And can you demonstrate that there would be, that biological production is the sole reason of that and of that detection, and whether there are any abiotic sources present? And then, do you have any independent signal coming from biology which can be detected? And I think we need to do this in a more systematic manner and understand that whether we can have a follow-up observation in time to see how the atmosphere changes in time, to understand the effect of atmosphere. So here you can see, if we look at the same spectra for an early Earth versus what the modern Earth looks like, it is changing. So if we go back to the same point and try to understand how the spectra possibly has changed within a year or two, we might have more clues to possibility of life on that exoplanet. And with that, I would like to quickly summarize that yes, life is a self-sustaining chemical system capable of Darwinian evolution, and we will accept that. But we need more information, and we need to be more thorough about defining life. And life over here is based on what life we know as on Earth. Life could be something beyond on Earth. Carbon may not be the basic molecule which would form the backbone of macromolecules. It could be something else. Water may not be the solvent. It could be sulfuric acid, or maybe something more reactive, maybe an alkane. So we will have to think about all those questions. We need energy, we need a solvent, we need encapsulation with a constant way of exchanging information from the environment. We need these bonds, not just covalent, but every bonds. We need eventually some form of replication for life to thrive in that environment. Of course, macromolecules are carbohydrates, lipid, proteins, and nucleic acids, but they're all made up of these basic elements, which is carbon, hydrogen, nitrogen, oxygen, and phosphorus, which is called SNOPs in short. Basic elements were present before life evolved on Earth based on stellar nucleosynthesis. So what life had to do was just bring them all together and make them relevant so that life could actually exist. And then the geological history of Earth is very dynamic in space as well as temporally. So it's a different field of study altogether. For me, the original building blocks of life can be defined by just how geochemistry of early Earth probably gave rise to first biochemistry, biological molecules, and how those biological molecules probably came together to be encapsulated in a more microbial life kind of a format. And extreme habitats are present pretty much everywhere on Earth. The first microbe survived only on redox chemistry, which was present around in the environment, carbon dioxide and hydrogen. And it was very late in the timeline when they actually started producing oxygen. So there was a very big gap of microbes which are surviving on anoxic in an anoxic environment. There are extreme habitats which are present. Habitability on Venus can be in the sweet spot in the atmosphere. There is, of course, a lot of carbon dioxide rich water present on Mars. There could be some signatures of life in the subsurface. Enceladus, Europa, they have very thick ice shell, and we need to study water rock interactions on the seabed. And habitability of exoplanets, we have to look into many criterions. The need of the hour is to incorporate how to identify these life detection scales during our habitability studies. And with that, I will be taking questions.
Okay, thank you very much, Dr. Yamini. I think that was a fascinating talk, and I hope the students learned some new things here. So while the questions are coming in, let's wait for those, but maybe I could ask one question to set the stage. Is in terms of our solar system, what are some of the most promising locations of for finding life, and what strategies should we adopt for maybe what kind of instruments should we build, what kind of the next best mission that we as a country like India should be investing in order to try and find something new in terms of finding life in the solar system?
Yeah, so I have a very interesting idea, and it is based on electron transfer. So we know that microbes can actually respire and oxidize electrodes. So they can give an electrochemical signal. So if we can design an instrument which can go to these water-rich environments, maybe icy worlds or or maybe in the environments where we can make use of liquid water on Mars, if we can sample that water or whatever the groundwater present in the planetary system and run them through the electrochemical reactor, will we be able to find something similar to this, like a carbon cloth which is associated with life, maybe some sort of microbial community which is present? So I think that would be and is an active area of research on how to identify microbes which might be present in these extraterrestrial systems, the close ones which are in the solar system.
Okay, fantastic. And with this, we have some further questions actually from the participants. Here's one from Shivan Kumar, who asks, why are we looking for life forms similar to the Earth? And there might be possibility of other kinds of forms of life.
Yes, so I did end up saying that, of course, life as we know it, we understand it. So it is easier as a research scientist for me to sort of base my instrument accordingly. But what I'm saying is electron transfer is necessary for life. There has to be transfer of electrons. The proton gradients are very important. You may say not proton gradients. There could be some other form of gradients, but transfer of electrons is very important. Life is electric in every case, in humans, microbe, anywhere. So if we can design an instrument which uses that feature of life to identify life in other planets or planetary bodies, that'll be great. We have to think out of the box. That is true. Hydrogen, carbon, and these are the most important cosmic elements which are present in the universe, in the cosmos. So carbon-based life is assumed to be present. Possibly there could be some other elements which can actually mimic carbon structures like silicon, but how much is silicon present in other planets? I think we'll have to identify those. So there are more questions which will arise if we start to think out of the box, which are great and valid questions, but we have to take baby steps. I think that is what my answer would be.
Okay, excellent. These are all very pressing questions, of course, but maybe getting into a few more related questions, you could talk a little bit more in detail, because a couple of students have this question on is life possible without carbon, and why is carbon so important for life? If we could dwell on this for a moment.
So I think carbon, we know that has the ability to form these nice covalent bonds, right? So which has formed the backbone of pretty much every macromolecule present on the life which is present on Earth. So again, I would say that it is the element and the kind of bond it will form which will define life. On Earth, carbon actually was there and present on the subsurface. And there was carbon dioxide, there was hydrogen, and there was these electrochemical gradients present, which initiated that process. Of course, in other planetary bodies, it could be different, but again, the way we learn and we know about the life on Earth is sort of how we are also looking for life outside the Earth. And I'm not saying that their DNA is also going to be similar than what we are. So I think we should focus more on electron transfer, the currents which we might get from these possible putative life. But yeah, how the life might look like could be completely different. But again, baby steps is what I would again repeat.
Okay, excellent. So moving on, here's a question from Balaji, who asks, can life exist on other planets like Saturn or Uranus? Maybe you could just give us some more insights into the kind of things that you presented earlier. I think that would be fascinating.
Yeah, I did not look much into whether life can be present in the Saturn and Uranus, but of course the icy world, which are moons of Saturn and Jupiter, there's possible life present. I'm really sorry for moving like that. Specifically for Uranus and Saturn, I think is what is being asked. My knowledge is limited in that sense. I know that there is methane present on Uranus. The methane is a signature, it's a biosignature. Presence of methane suggests carbon dioxide combining with hydrogen to form methane. It could be, it cannot be. There could be olivine just breaking down into methane. So there could be life, there could not be life. I think we'll have to really build instruments to identify and sample the environments. So Europa is building radar. They are identifying via mass spectrometer what kind of chemicals are coming out from these plumes of Enceladus and Europa Clipper. Yes.
Okay, there is one more question, this time from Ningtojam Singh, who asks, how accurate really is the data that we are able to interpret as an exoplanet being Earth-like? That may be more in my area of expertise, but we'll hear Dr. Yamini what you have to say on that.
There are various ways of defining Earth-like, I think. So whether the orbit, remind me the question. Are you talking about whether the data itself is wrong, or? Sorry,
yeah, I mean,
again,
how believable is the data, and how accurately we might be able to say that this planet is Earth-like?
Believability of data, I think, Kunal, you can talk about, but I think the way Earth-like planets are identified, I think there are various ways of identifying whether the radius of the orbit is equal to the Earth. Now, whether the radius, what is the error bar in identifying the radius of the orbit of Earth depends upon the emission spectra from these planetary bodies, and the mass. I am not sure what the relative error bar over there is, but yes, Earth-like requires a lot of things. So again, whether there can be life on Earth, on planetary bodies which are within the size of the Earth, whether they have the atmosphere of the Earth, whether they have the tectonic dynamic tectonic plates like the Earth. I think there are just too many things to consider to just the mass and the radius would not be sufficient. It's Earth-like in mass and the radius of the planet, but not maybe the environment. So
right. So I may add a couple of sentences. Yeah, I just may add a couple of sentences to that by responding as, yes, you said mass and the radius is one of the aspects. Then you'll need to look at the host star, how far it is from the host star, what kind of a host star is it, and then what you would look at is the albedo of the planet, which gives some information on the atmosphere, right? Or you can look into those kinds of plots that he showed on transmission spectra, right? Does it have the right kind of spectroscopic signatures where we can predict, yes, there is water in the atmosphere, and then there is carbon dioxide in the atmosphere. Are there any signatures of biological species, right? Like phosphine was mentioned as one of the examples, and methane is another one. So do we really see these kinds of signatures in the spectrum of the atmosphere of the planet? I think all of these go really into saying for sure that this is more Earth-like than Jupiter-like, and so on. Yeah. Okay, so I think those are the questions that we had. And let's thank the speaker, Dr. Yamini Jangir, again for this very fascinating topic and very fascinating presentation. Okay, thank you everyone for tuning in, and thank you to the organizers.
Thank you so much for being here.
Thank you, Professor Kunal, for very nicely moderating this session. And also my thanks to Dr. Yamini Jangir for this inspiring as well as very informative lecture. Actually, we are in the study phase. It's a new area which is emerging in our country, and also we are also looking forward for getting more and more information in this area. Anyway, you have guided us in that way. Thank you very much for both of you. And
all right,
to the
thank
participants,
you. Have a good day, everyone.
Thank you. And to the participants, we will meet again tomorrow in the same time at 3:30. Tomorrow also we are having 2 lectures. Please stay with us tomorrow.